In this video, we're looking over balancing reactions as review and net ionic equations. So you should already be able to balance reactions and use solubility rules, but by the end of the video, you'll need to know which solubility rules to memorize and use those to form solid precipitates and write net ionic equations. So the question of the video that we're going to answer by the end is lead 2 nitrate is dissolved in a sample of water, and lead ions are particularly unsafe for human consumption. So what are some ways to get the lead out? Will filtering work? So you can see our little pictures where there's like lead in the solution, right? We want to get it out of the solution. So let's talk about some reactions. Reactions in chemistry are written with reactants on the left and products on the right, and the coefficient tells you how many of those particles you need in order to react completely. For example, if you were going to make cake from a cake mix box, you would take one box of mix, and if there's not a 1, you assume a 1. 2 eggs and a cup of water, and those are your reactants, and then once you bake it, which might be your arrow, you make your cake. It's similar with chemistry in that if I want to make aluminum oxide or aluminum rust, I would need 4 aluminums for every 3 oxygens. That's the recipe. To make, that's what the arrow is, 2 Al2O3s. So anything on the left are the reactants, and anything on the right are the products. In a reaction, atoms and molecules cannot appear or disappear. The mass has to stay constant from the beginning to the end, and therefore we need to show a conservation of mass. So if you look at this reaction for water, water is comprised of hydrogens and oxygens, and hydrogens come as 2s as well as oxygens. They are kind of stuck together as twins or diatomic molecules. But if you look at the way the reaction looks, it looks like the oxygens lost. It went from 2 oxygens to, after the arrow, only 1 of those. So that's not going to work for us. We also can't just squiggle in a little 2 at the end of that, make it H2O2, because that's not the same chemical. H2O is something that you might drink, water. H2O2 is hydrogen peroxide, what you might use to disinfect wounds, and if you drink enough of that, you will die. So we don't want to change what the chemical is. We want to change how much of it we have. And so the way we do that is put coefficients in front of the number of the substances. How many of each one would you use? And since our oxygens are the ones that were giving us trouble, I'm going to put 2 waters in front. That 2 corresponds to now there's 2 oxygens, and it matches the 2 oxygens we started with. But it also affects the hydrogens. It affects everything after it. So now I'll also have to put a 2 in front of the hydrogen side, which means I had 4 particles of hydrogen and 2 oxygens to start, and I also have that to end. So let's try some more examples. In this one, you can see nothing is balanced. I started with 2 nitrogens, and now I only have 1. I started with 2 hydrogens, and now I have 3. So an easy fix for nitrogen is to put a 2 in front of the ammonia, 2 N's, 2 N's. But that changes our hydrogens to 6. 2 times 3 is 6. It's like writing NH3, NH3. So if I have 6 H's, I will also need 6 H's on this side. 2 times 3 would give me 6. That's right, writing H2, H2, H2. Let's try that again. Here, we can see nothing again is balanced. 1 lithium, 2 oxygens, 1. So I'm going to put maybe a 2 in front of lithium, but you'll see that 1 doesn't work out. I need to put a 2 in front of lithium oxide to match the 2 oxygens here, which means I really need to put a 4 in front of lithium. You might want to do these in pencil because sometimes you wind up amending your first thoughts. Here's some harder examples. When you see things that had polyatomic ions or clusters of compounds, you might want to treat it as a cluster. So there's 1 lead, 2 clusters of NO3, and only 1 cluster of NO3 here, so we're going to put a 2. 2 Ks, and now 2 Ks. 1 cluster of CrO4, so I can treat it as one big thing. Or you can do it individually. There are 2 Ns, 6 Os there, so 6 Os there, 1 Cr, 4 Os, 4 Os. All these other blanks can stay 1s. Let's do it one more time. Here's a combustion example. There are 4 carbons, so 4 carbon dioxides. 8 hydrogens, so 4 times 2, so 4 waters. And with oxygen, be careful because they're all over the place. I have 4 here times 2, so 8 in the carbon dioxides, and another 4 in the water. 8 plus 4 is 12. So in order to get 12 here, 2 times 6 is 12. Some people like to write notes as they're learning this. Make sure you're okay with this before you move on. So solubility is something we also talked about last year. It's the ability to dissolve in water depending on factors such as polarity, which we define later, chemical nature of the ions and their attractive forces, and they have varying degrees of solubility. Substances that are characterized as mostly soluble will dissolve in water under most conditions, and they will have a limit. So like there's a limit to how much salt you can get in your water, but mostly it dissolves, right? Moderately soluble ions are soluble depending on the ion they're bonded to. So sometimes they dissolve with chloride, but they don't dissolve with fluoride or something like that. Insoluble substances may not actually be insoluble per se. It just means they're not visibly soluble. So there might be some particles that do dissolve, but to our naked eye, it looks like everything just sunk to the bottom. So they're only dissolving so few that maybe we can calculate it later in the year, but for now we're going to assume that nothing dissolved. So what we're going to use instead of table F from last year, we're going to memorize some solubility rules, but they're quite quick and easy. What you're going to know is group 1 ions such as lithium, sodium, potassium, rubidium, and cesium, the group 1 on your periodic table, with those +1 ions are always soluble. In addition, we have ammonia, NH4+, which might be familiar from our acid-base unit, acetate, C2H3O2-, which is one of my favorite ions, and nitrate, NO3-. These chemicals, what you might notice is they're all +1 or -1 ions. So those 1 ions seem to be pretty well dissolved in water, and anything they're reacted with will be dissolved in water. So anything that's not on this list, we're going to consider to be mostly not soluble or insoluble. So note, again, these are +1 or -1 ions. If they're with any other ion, they're soluble. For the purpose of the AP exam, all other substances are considered insoluble, unless they tell you in the question. They're like, oh, we got to dissolve somehow, maybe by heating it up and breaking it up and all these crazy things, right? Notice again, these are yellow, so that means you have to memorize this list, and you might pause it to write it down. So let's just see if you're good at this. Are they soluble or insoluble? I'm going to go down the list. You might pause it and check. So NaI, because of the Na is soluble. K2SCO3, because of the potassium, group 1 is soluble. Aluminum hydroxide doesn't have it on those ions, so it's insoluble. Same with lead sulfate, PbSO4, insoluble. AgCl doesn't have any of those ions we listed, insoluble. NH4, bing, 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 S, is soluble because of the NH4. Aluminum phosphate is insoluble. Sodium, group 1, so Na2SO3, soluble. Magnesium oxalate, insoluble. To the top, lithium oxide, soluble because of lithium. Calcium chromate's insoluble. Barium fluoride's insoluble. Magnesium chlorate, insoluble. Cesium, group 1 ion. Cesium carbonate, soluble. Rubidium acetate, double soluble. And strontium nitrate, because of the nitrate, is soluble. So really, again, if you know that these things mean they're soluble, you're looking for them and writing S. And if you don't have them, you're writing I for insoluble. The reason we need to know that is because we want to be able to track what's happening during a reaction, and these things, if they dissolve or not, might come up in our reactions. So molecular equations are frequently used to show how chemicals are mixed in a reaction, but not actually what's really reacting to our naked eye. The net ionic equations are simplified forms of the molecular equations that eliminate what we call spectator ions and only show the species that react. So molecular equations such as BaCl2 and Na2SO4 double replaced to make barium sulfate and sodium chloride, but not necessarily what actually we can see in our beaker. You're not going to see two new things form. So what we're going to do is we're going to ionize anything that was soluble, thus the list. In this case, barium chloride was considered soluble. I might have said it in a former part of the question. I just left it out by accident. So we're going to separate that. Na is soluble, right? So separate it from the sulfate. After the arrow, BaSO4 is not soluble, and sodium chloride is soluble because of the sodium. What you notice is the things before the arrow are all ions, and so that means when they're in the water, you can't see them, right? They're dissolved in. And after they mix, barium sulfates after the arrow is stuck together. That means it precipitates or forms a solid, and that solid falls to the bottom. Note that the sodium and the chloride ions stayed in the solution, and they stayed invisible. So that means the sodium and the chlorine are going to be canceled out because they are super soluble spectator ions. And the only thing that really reacted was barium with sulfate to make barium sulfate. The difference is barium and sulfate in the ion form means that they were dissolved because it used to be with barium used to be with chlorine and sulfate used to be with sodium, making them dissolved. But once they break their partners and rearrange and they find each other, they form a solid. So for practice, write out the ionic form like I did, breaking down only soluble aqueous substances and cancel and rewrite. Don't worry about writing phases, although it might help you to write the phases if they're a solid or a gas, and make sure you don't ionize those solids and gases. The only things that ionize are aqueous soluble things. The AP will always give reactions that have a net ionic equation, but your exercises in a textbook or online might not. So if every substance ionizes, the reaction doesn't seem to occur. So how will you know if a substance is aqueous, liquid, solid, or a gas? Generally, if it's insoluble, it's a solid. If it's just a pure metal, it's a solid. If it's dissolvable, soluble, it's aqueous. A liquid that you should watch out for is water. And a gas would be covalently bonded. So substances are only aqueous if they're soluble. All insolubles or metals contain metals or solids or insoluble. And most compounds that do not contain metals are either soluble or gaseous. So let's practice some examples. First, you need to know how to double replace. So I'm going to write the aluminum and the sodium separate and switch their backs. Aluminum is the hydroxide. Check your ions. Aluminum is +3 and hydroxide is -1, so it's AlOH3. The sodium is the nitrate. Na is +1, group 1, and NO3 is -1. So that is the way it is. And then we want to balance the reaction. Since I had 3 nitrates, I want to have 3 nitrates on the right. That gives me 3 sodiums, so I'm going to put 3 sodiums on the left. And that gives me 3 hydroxides, which matches my 3 hydroxides on aluminum hydroxide. Now that we have a full reaction that's balanced, we're going to ionize. Notice we ionize anything that's soluble. The aluminum and nitrate break up because it's soluble due to nitrate. Sodium and hydroxide break up because of the sodium being soluble. And at the end of the equation, sodium and nitrate stay broken up because they are also soluble. The one that stayed together was aluminum hydroxide because it doesn't have any of those soluble species. We're going to cancel things that are like on both sides and rewrite it as aluminum from one chemical and hydroxide from another came together to form a solid. That is our net ionic equation. If we do another one, remember, you're going to switch the back. So potassium will get a nitrate. Check your charges. K is plus, NO3 is minus. It's a perfect pair. Calcium is +2 in group 2. Phosphate's -3. So we have some finagling to do to balance the charges. We want to see if we have the correct number of substances. So on the left, I have 6 potassium, so I need 6 potassiums on the right. I also have 3 times 2 or 6 nitrates, so that works out, and 3 calciums, which is good, and 2 phosphates, which is good. Now that we have a balanced equation, we're going to ionize things that are soluble. I'm going to ionize K and nitrate, because those are soluble, and especially K and nitrate. But the one that doesn't have any of those soluble species is calcium phosphate, so I'm going to leave it together. We're going to cancel the 6 Ks and the 6 nitrates because they're the same on both sides, and rewrite that 2 phosphates from one chemical that were dissolved and 3 calciums from another chemical that was dissolved came together to form calcium phosphate as a solid particle that fell to the bottom. Back to the question of the video, lead 2 nitrate is dissolved in a sample of water. The lead ions are particularly unsafe, so how do we get them out? Would filtration just work? If you filter it, anything that's homogeneous or you can't see its particles, the filter can't see it either. So the filter is not going to help you get out those those soluble things, right? What we need to do is find a way to make the lead insoluble. Right now it's soluble because it's with nitrate. So if we can add something that will make it not nitrate and switch out the nitrate, we might be okay. So mix with a different anion to form a precipitate. I chose to pick NaI because I had it on hand. And if I double replace, I get Pb with the I. Notice Pb is +2 because it was 2 nitrates here, so it's also going to have 2 iodines. And the sodium goes with the nitrate +1 to -1. And maybe you want to balance it so it's reacted. So you notice that I didn't balance it here, and when I ionize it, I get lead and 2 nitrates, a sodium and an iodide because they're soluble, a PbI solid because it's not soluble, and Na and NO3 separate because it is soluble. And when I go to cancel, I can't cancel out the NO3s because they're currently not the same number. So that tells me I forgot to balance. So I might go back and put in a 2 there, but that means I also had to put a 2 in for Na, and a 2 in for Na on this side, and a 2 in for this iodine, which really means if I had done it in the beginning, there would have been 2s up there. So I really recommend balancing first, but you'll catch yourself if you didn't balance. Now I can actually cancel the nitrates and the sodiums. For a final answer of lead ions were in the water, we put in some iodine ions to get them out. The PbI2 solidifies and falls down to the solution, and now because I can see it as a solid, the PbI2 will come out of the solution, right? But what will still be in the water? There will still be nitrate ions and sodium ions in the water. So you only want to add as much as you need to get precipitate out. You don't want to have too much excess. At this point, you should memorize your solubility rules, use them to find the solid precipitates, and write net ionic equations.